Hello, so we're going to continue the conversation of acid and bases, but we are going to focus primarily on strength and concentration. So we talked about that water ionizes, right? And we talked about how when water ionizes, it generates a hydronium ion and a hydroxide ion. And because they have the same concentration, water is neutral, right? So that's kind of the primary focus in here is that acids are going to be substances that when dissociate, when they kind of break apart, they're going to generate either hydronium ion or a hydrogen ion. And the base, on the other end, are substances that are going to generate hydroxide ion, right? And water actually does both of them. That's why water has equal concentration of both of those ions. So another thing that I need to go over with you guys before we begin is we need to introduce two vocabulary words. One I actually already used, it's called dissociation. So it's the breaking apart. Okay, so when an acid or a base separate in water. And even water can dissociate, right? And then I want to introduce something else to you guys, a conjugate acid and a conjugate base. So whenever an acid donates or generates a hydronium ion, the acid changes into a base, and it's called a conjugate base. Okay, and whenever a base accepts a hydronium ion, it becomes a conjugate acid. Okay, so you're gonna hear that term quite often. All right. So when we talk on acid and bases, we talked about how to identify them, but now we need to talk about strength. So when we talk about strength and when we start to comparing either acids or bases with themselves, we need to think about two things. One is concentration, how much of it is available, right? That will determine the strength. The higher the concentration, the stronger it is. For example, bases, the more concentration of a base there is, the higher the pH. The more concentration of an acid is available, the lower the pH. The second thing, not to confuse, the second thing that's important is strength. We call it strength of acids, strength of bases. So not all acids dissociate completely. So we call strong acids, acids when put in water, they just break apart. Okay, they dissociate fully. Whereas weak acids, they kind of do it, but they do it very mildly. Okay, some of it dissociates, but not all of it. Okay, so what does it look like? So a strong acid, this is a strong acid. Let me present, see if you can see it bigger. Okay, there we go. So a strong acid, right here, the hydrochloric acid is very strong. In the presence of water, it generates hydrogen ion and chlorine ion. The chlorine ion is the spectator, right? Spectator base. But anyway, notice how this reaction is irreversible. Okay, once it gets in the water, it fully dissociates, and it should look something like this. Whereas a weak acid, I believe this is acetic acid. In the presence of water, you still generate your expectator, I'm sorry, not expectator, your conjugate base as well as your hydrogen ion. Okay, so it's doing what acid's supposed to do. However, it's not going all the way. The reaction is reversible. Okay, and it would look something like this. So the same thought process applies for bases. So here is an example of a strong base. I know it's a base because it's generating hydroxide ion. Here's my conjugate acid. Right? Notice the reaction is irreversible, therefore is a strong base. And here you have ammonia interacting with water, forming ammonium ion, right? And then I know again it's a base because it's a hydroxide ion, and again it is reversible, does not fully dissociate. Okay, so those are important things for you to know. All right, so we're going to go through a simulation, and I want to show you this slide. You can use this as a key. So when I do the simulation and you see that you're going to see different symbols, you know what they represent. Okay, so I won't go through each one of them, but if you need to refer back, you have access to these slides, right? So you can go back and be like, what is this again? So you know what it is. So let's start the simulation. All right, so you have a container here. It's a liter container, and we're starting with water. Okay, and this is what's the reaction here. This is the self-ionization of water. And we know water is neutral, so no surprise here. The pH of water is 7. Okay. Let's begin by looking at a weak base. So this is a weak base. Notice all of a sudden the pH dropped from 7 to 4.5. Okay. The reaction that's taking place here is you have an acid dissociating in water to form your hydronium ion, and the reaction is reversible. Okay. Now let's compare this weak acid with the strong acid. Here you have a strong acid. Here you have a strong acid. The pH dropped from 4.5 to all the way down to 2. Okay, so it was a drastic change in pH. Notice here that again you have an acid dissociating in water. Again, you have your hydronium ion. However, the one thing I wanted to point out is that you don't see any acid. Right, you only see those two species, right? You only see the A minus and you only see the hydronium ion. You don't see any of this, where this is not the case with a weak acid. A weak acid, you see the 3 of them. The water is not shown just for simplicity's sake. So you see the HA, it's right here. You see the A, and you see the hydronium ion. So you see all the 3 species here. Because again, it's not fully dissociating. That is not the case for a strong acid. All right, the other thing besides, obviously you can't see this, right? And because it's probably clear, or you can't really see this in a molecular level. Besides pH, there's other ways for us to determine whether it's a weak or a strong acid. So let me give you an example. Instead of pH, what if we use ability to conduct electricity? So I'm going to put this here. This is a conductor, right? This closes the circuit. And we're going to measure the ability to conduct electricity by seeing if the light bulb lights up or not. Okay, so this is water. Pure water really does not conduct electricity. Let's look at a weak acid. A weak acid does, and the reason why it conducts electricity is because it has very strong charges, right? You have the negative here and the positive here, and remember that the ability of conduct electricity has to do with the strength of the ions. So it conducts electricity. However, if you compare that to a strong acid, okay, so a strong acid conducts way more electricity, and again, because it's fully dissociating, so there's more of it. So you can think about it that way. All right, so the story with the bases is very similar. So let me reset. Again, starting with water. Bases pretty much follow the same setup. Let's start with a weak base. Okay, so you have a base dissociating in water. You have your conjugate acid and you have your hydroxide ion. That's your key here to know that you're dealing with a base. And you see all the 3 species. You see the yellow dot spheres, you see the blue ones, and you see the gray ones. So all 3 species are there. Okay, and water is there too. It's not shown for simplicity's sake. Okay, notice that the pH of water was 7, and with this weak base, it went all the way up to 9.5. Okay, let's switch from a weak base to a strong base, and you see the pH jump significantly. Right, and let's see why that's the case. Well, this is your strong base, right? And it is dissociating in water, right? So for some reason they don't have the water here to form your conjugate acid and your hydroxide ion. You do not see this here. You see, you don't see any gray spheres here. That's because it's fully dissociating. Okay. And as you may guess, the ability to conduct electricity is going to be very similar, right? So let me switch here. Conduct electricity quite a bit. Conduct electricity very little, and then even less, right? So that is the ideas that you need to make sure that you understand. Now I need to mention one more thing. So we talked about strength. We also need to talk about concentration. So let's think about concentration for a moment. So let me choose an acid. Let me choose a pretty high concentration. Let me push the concentration to 1 molar. Notice here moles per liter, that's 1 molar. All right, so I have a weak acid. Okay, so I'm going to measure the pH of this weak acid. And it's about 3.5. Okay, so again, with the same concentration. Notice that when I decrease the concentration, what I'm decreasing is the amount of HA, or the amount of acid, right, available to dissociate. So it makes sense, and you can see the pH is increasing because it has less and less hydrogen ions or hydronium ions. So what I'm doing when I'm increasing concentration, I'm increasing the concentration of HA, which is causing to dissociate more. Remember Le Chatelier's principle, I'm increasing this, therefore the equilibrium is shifting to the right. And if the equilibrium is shifting to the right, it makes sense that the pH is lowering it down. Okay, low pH means strength, high strength. So there we go. If we go all the way to 1, you can see this. There's a lot of acid here. Not all the acid is dissociated, but that's what you get. Keeping the concentration absolutely the same, let's just switch from weak to strong. Okay, the pH all of a sudden drops significantly. This is pretty strong. Notice that there is no HA here. Okay, because as soon as it hits the water, it dissociates, it does not turn back, there's no equilibrium. All you see is the conjugate base as well as the hydronium ion. And the same thing applies here. So as you decrease the concentration, you're removing the amount of hydronium ions, right? And you're increasing the pH. So that is the idea behind, right? You're decreasing the pH as you're increasing the pH as you dropping the concentration of hydronium ion. Remember that concentration of hydronium ions and pH are irreversibly proportional. As one increases, the other one decreases. Right? So one point I wanted to make here is that when you're comparing two acids or two bases, there are two things you need to be aware. You need to be aware of their concentration, and you need to be aware of their strength. So for example, let's go back to, so here in a strong acid. If I have very little of the strong acid, in other words, very little concentration, very, very small concentration, all the way over here, the pH is 3. If I switch this to a weak base and I increase the concentration significantly, I get 3.5. So the pH is still higher, so it's still a weaker acid, but much less, right? So the two things that are important is both concentration and strength. The same thing, I won't repeat this, but the same thing, let's repeat it. The same thing applies for bases, right? You have, let's start with a weak base. In a weak base, again, you're increasing the concentration of the base. According to Le Chatelier's principle, the equilibrium shift this way. As the equilibrium shift this way, you actually increasing the concentration of OH, right? And decreasing the concentration of H. So as you decreasing the concentration, you're actually lowering the pH. Okay, so for bases, the pH is proportional to the concentration of OH. Okay, so think about that. And you can, if this is kind of tough to follow, you can always come back to the simulation. I have the link for you, so you can just play on your own and you can see how that works. Okay, but the same idea applies for bases. And then you can go for a strong base where there's no equilibrium. It fully dissociates. And again, the same principle applies. If you lower the concentration of the base, you're also lowering the pH. Okay, so just to summarize, I have few things here. So this statement, let's just look at it for a moment. Strong acids have lower pH than weak acids. In general, yes, not always true. It really depends on the concentration. If they both have the same concentration, then yes, that is true. Okay, but you need to be aware that the concentration also plays a role. Okay, so, and this is just a reminder. I won't go through this because this is exactly what we're doing, where we're able to change the concentration of the weak acid to be very close to the concentration of a strong acid. Okay. What ways distinguish a weak acid from a strong acid? Take a look at those options. So let's look at each one of them. A weak acid does not react much in water. Strong acids completely react. That is very true. Okay, so we keep that one as true. A weak acid is more dilute than a strong acid. Well, that's not always the case. That has nothing to do with weak or strong. Dilute, it has to do dilution or concentration. It has to do with dilute or concentrated. It has to do with concentration. It has nothing to do with strength. Okay, so that is not true. It can be, but that statement is not true. A weak acid has a higher pH than a strong acid. Again, we're assuming that if they're the same concentration, that is correct. Okay, and then so assuming that they have the same concentration in here, I would say A and C is correct. But I would definitely make sure that to state here that both concentrations are correct, or both concentrations are the same. Alright, so you can always return here and take notes. The link for the simulation is right here, and I have this slide, so you can actually play along to see if you can, if that helps you follow along this content. And now you should be ready to move on to the lab.